to today's class. We are going to be learning about formation of differential equations, part 1. Now, there are two key steps in solving or in forming differential equations. The first one is that you have to differentiate the primitive equation a number of times corresponding with the number of arbitrary constants present in that primitive form or primitive equation or primitive function. So this means that given a primitive equation, for instance, you're going to count the number of arbitrary constants that you can see in that primitive form. Now you're going to differentiate that particular primitive form according to the number of arbitrary constants present. If there is one arbitrary constant, you're going to differentiate one time. If there are two arbitrary constants present, you're going to differentiate two times, and so on and so forth. Okay, then the next step is you're going to solve the system of equations that arise by eliminating all the arbitrary constants and leaving the output only in terms of derivatives, independent variable, dependent variable where necessary. So you're going to attempt to solve the system of equations that arise when you differentiate your primitive equation a certain number of times depending on the number of arbitrary constants present. So your objective is to eliminate all arbitrary constants, then leave the output only in terms of derivatives or mixed with dependent variables and independent variables, okay, where applicable. So we're going to be seeing some examples and we'll get to understand much later in the course of these lectures what these arbitrary constants actually stand for. Okay, so let's move on to example 1. Okay, here we go in example 1. So the objective is to obtain the differential equation from the primitive form y is equal to a exponential 2x plus b exponential 3x. So how do you solve something like this? So let's find out together. So for this particular example, I'm going to show you 3 ways of obtaining differential equation, okay, still built on the concepts I introduced earlier. So first of all, to solve this differential equation, how many arbitrary constants can we see? I can see 2 arbitrary constants, a and b, okay. So I'm going to differentiate 2 times. So since there are 2 arbitrary constants, I'm going to differentiate 2 times like this. Now y prime is equal to, when you differentiate this particular side, what are you going to get? 2a exponential 2x. Is that okay? I hope you still remember your calculus. Plus, when you differentiate this side, you're going to get 3b exponential 3x. So assuming this is equation 1, this is equation 2, and this is going to be our equation 3. So y prime is first derivative, okay, and y prime is second derivative. So when you differentiate this part again, you're going to get 4a exponential 2x plus, differentiating this part again, you get 9b exponential 3x. So this is our equation 3. Okay, so we are going to be using the likes of y prime to stand for dy dx, and y prime actually stands for the 2y by the x squared, and so on and so forth. Okay, so please take note of these terminologies. Now, because this particular primitive form had 2 arbitrary constants, you see that we have differentiated 2 times in equation 2 and equation 3. So this is the convention. So depending on the number of arbitrary constants you have, you're going to differentiate. So we have satisfied the first step. The second step is now to solve this system of equations that arise. This system of equations, we want to solve it in such a way that we're going to eliminate all the arbitrary constants. And to eliminate all the arbitrary constants, we want to express our answer in terms of only derivatives and perhaps dependent or independent variable where necessary. So let's see how this goes. So I said I'm going to show us 3 ways, right, of solving it. So let's dive into the three way of solving this particular problem. Okay, previously, these are the system of equations we came up with after differentiating this particular primitive form 2 times. Now, the next step is to eliminate the arbitrary constants, okay, a and b. So this is how we are going to do it. Now, I'm going to say equation 2 minus 2 times equation 1. So from the left hand side, you have y prime minus 2y is equal to, of course, 2a exponential 2x, okay, plus 3b exponential 3x minus 2y. So this is y, a exponential 2x plus b exponential 3x. So this is equal to 2a exponential 2x plus 3b exponential 3x minus 2a exponential 2x minus 2b exponential 3x. So this is our y prime minus 2y. So y prime minus 2y is equal to 2a exponential 2x cancels out 2a exponential 2x. We have 2b exponential 3x being subtracted from 3b exponential 3x, and that gives me b exponential 3x. So this is equation 4. Okay, so if you repeat the same procedure by saying y prime prime minus, let me choose the second one, y prime prime minus 2y prime. So if we repeat it carefully by observing the left hand side and the right hand side, so to do that, you can see that if you multiply y prime by 2, we'll have 4a exponential 2x plus 6b exponential 3x. So I'm just going to say that y prime prime minus 2y prime, okay, this particular term and this particular term multiplied by 2, they are going to be cancelled out. So I'll now have 9b exponential 3x minus 6b exponential 3x, which gives me exactly 3b exponential 3x. Okay, so this is equation 5. Are we together? Alright, so I'm just going to try to squeeze it here to manage the board. So the next step, I'm going to divide equation 5 by 4 by equation 4. So when I divide equation 5 by equation 4, I'll have y prime prime minus 2y prime all over y prime minus 2y is equal to 3b exponential 3x divided by b exponential 3x. So this cancels out this. Are we together? So I'm now left with y prime prime minus 2y prime all over y prime minus 2y is equal to 3, so over 1. So when you cross multiply, I'm going to have y prime prime minus 2y prime is equal to 3y prime minus 6y. Okay, when you cross multiply, and when you rearrange, you have y prime prime minus 5y prime plus 6y is equal to 0. So this becomes the answer. This is the differential equation that is formed when you eliminate the arbitrary constants and when you follow the steps. So I'm going to show you another way to obtain this particular answer in the next step now. Okay, so previously we got from y is equal to a exponential 2x plus b exponential exponential 3x. We got our differential equation to be y prime prime minus 5y prime plus 6y equal to 0. So I want to show you another way of getting it. So I'm going to call this one using the determinants method. So the determinants method, so using the determinants method, as usual, first of all, you're going to find, okay, y is equal to a exponential 2x plus b exponential 3x. Now of course y prime is 2a exponential 2x plus 3b exponential what 3x, and y prime prime is equal to 4a exponential 2x plus 9b exponential what 3x. Now if we rearrange this particular equation in this form, if you rearrange this particular equation in this form, for instance, y minus a exponential 2x and minus b exponential 3x equal to 0. So we have also y prime minus 2a exponential 2x and minus 3b exponential 3x equals to 0. And finally y prime prime minus what 4a exponential 2x plus 9b exponential 3x. Sorry, it's a minus over there, sorry about that. Minus 9b exponential 3x equal to 0. Now I'm going to obtain a determinant matrix from the coefficients of everything here on the left hand side. So this is how you're going to form your determinant matrix, like this. So you have y, then you have minus 1. So in this forming of this determinant matrix, the only thing that you're kind of striking out is this over here. You're striking out these terms, okay, striking out these terms, then you're choosing what you're left with. So you have y minus 1 minus 1. On this particular line you have y prime minus 2 and minus 3. On this particular line you have y prime prime, you have minus 4, and you have minus 9, okay, and this is equal to 0. So by the time you solve this particular determinant and you calculate the determinant equal to 0, you will still get the same answer. So I'm going to expand this determinant along the first column. I'm expanding this determinant along this first column. So I'm going to start with this term over here. So remember, plus minus plus plus minus plus. So you can actually expand the determinants from any row or column that you want, and you can actually scatter the position as far as you obey the sign conventions. So I'm going to start from this term over here, okay. So we have y prime prime, so I'll get the minor of this y prime prime, which is actually this term over here, this times this minus this times this. So for instance, y prime prime, then minus 1 times minus 3 is actually 3, then minus 2 times minus 1 is actually still 2, okay. Then you now do minus y prime into, so you get the minor of y prime, which is going to be minus 1 times minus 9 over here, which is still 9, and finally minus 4 times minus 1, which is still 4. Then you do your plus y into, then you get the minor of this one, which is minus 2 times minus 9, 18, and minus 3 times minus 4 is 12. So everything equal to 0. So by the time you simplify, you have y prime prime minus 5y prime plus 6y equal to 0. So using the determinant method, we have been able to obtain the same answer that we actually obtained when we used the normal elimination or substitution method. So there's still yet one more way to solve this particular equation, and we'll jump over to another example. Okay guys, welcome to the third approach of solving this particular problem. Remember, we have a given primitive form y equal to exponential 2x plus p exponential 3x, whose differential equation is y prime prime minus 5 y prime plus 6y equal to 0. Now I want to show you a really short way of solving this particular problem, and that's is using an approach called auxiliary equations. So using auxiliary equations, okay, so this step is using auxiliary equation method. So using auxiliary equation method, the concept is first of all to look at the exponential terms that are present in your primitive forms. Okay, that is just what you need, the exponential terms. Now you're looking at the constants in the argument of the first exponential. So m1 is equal to 2 in this case. So in this particular case, you have m2 is equal to 3. So if there are more exponential terms, then you're going to go on with your m3, m4, and so on and so forth. So since they are just two exponential terms, this is what I have. So what I'm going to do is I'm going to assume a general equation in this way: m minus m1, okay, then m minus m2 is equal to 0. So this is my auxiliary equation. So this is the general form of any auxiliary equation that you're going to be using if you're solving it according to these steps. So we have it, and it's always going to be a minus, okay, it's always going to be a minus. Now it's going to be a minus, but take note, m1 and m2 sometimes they might not be minus, they might not be negative, they might be plus. So in that case, the minus sign will affect whatever the signs of m1 and m2 may be. Okay, so for this case, I have m minus m1 is 2 and m minus m2 in this case is 3 is equal to 0. So I'm going to expand. So this is m square minus 2m minus 3m plus 6 equal to 0, and this is m square minus 5m plus 6 equal to 0. So this is my auxiliary equation over here. So for this auxiliary equation, how to round it up is that you're going to convert every m square to y prime prime. You're going to convert every m to y prime, and we're going to convert every m raised to the power 0, which is still the same thing as 1. You're going to convert it to y. So in this auxiliary equation, we'll have y prime prime minus 5y prime plus, 6 is still the same thing as 6m raised to the power of 0. So in this case, you can just call it 6y equal to 0. And with this auxiliary equation approach, you have obtained just about the same answer that you obtained using the first two methods. So the choice of which method to use depends on whether you're given this particular question in an objective scenario or in a theory scenario. I would recommend that if you're given this particular question in a theoretical scenario where you're to solve and show your workings, you should use the first approach, or you should use the second approach, that's method of determinants. Okay, so you can only use this auxiliary equation method to verify your answer, because the auxiliary equation method works like almost all the time. So it's just a method of verifying your answer. And when we start solving second order differential equations, you understand the importance of this auxiliary equation. So I'm going to look at one more example, and that will be all for the first part of forming differential equations, part 1. Alright, now look at the second problem. You want to form a differential equation given this primitive y is equal to a exponential bt. So of course we're going to ask ourselves, how many arbitrary constants are there in this primitive? There are 2 arbitrary constants, So we are going to differentiate 2 times. Is that okay? The 2 arbitrary constants are a and b. So a and b are arbitrary constants. So let's go. So we have y is equal to a exponential bt. Okay, so this is equation 1. So when we differentiate, y prime becomes ab exponential bt. So this is equation 2. When we differentiate again, y prime prime is equal to ab squared exponential bt. So this is equation 3. Is that okay? So how do you now resolve this particular equation? So this is how you normally resolve it. So let's say we divide equation 2 by 1. So equation 2 divided by equation 1. So 2 divided by 1 gives me y prime over y is equal to a b exponential bt divided by a exponential bt, and clearly this is just going to be b. Now this is equation 4. So I'm going to divide equation 3 by 2. Next step, so we are going to get y prime prime divided by y prime is equal to a b squared exponential bt by ab exponential bt. So this is also b, equation 5. So you can see that equation 4 and equation 5 have the same right hand side. So in other words, y prime over y is equal to y prime prime over y prime. Are we good? So when you resolve this particular equation by solving the or cross multiplying, you have y prime prime, okay, is equal to y prime all squared. So in other words, we can have y prime prime minus y prime all squared is equal to 0. So this is the differential equation for this particular system over here. So this is the differential equation. So I hope we all understand how to approach differential equation problems right now. So you just need to identify how many arbitrary constants in the primitive form, and you're going to differentiate according to the number of arbitrary constants present, and you're now going to solve in such a way as to eliminate the arbitrary constants. Take note, in your final answer, the arbitrary constants must not be there anymore. Your final answer, which is a differential equation, should be in terms of the derivatives, the dependent variable, or sometimes the independent variable alone. Is that okay? So thank you very much for watching this long tutorial. In the next video, I'll show us more on forming differential equations. Don't forget to like and subscribe and share. See you in the next video.